All right, in this video, we're going to be learning about micrometers, specifically the outside diameter micrometer or outside mic or OD mic, depending on who you're talking to, what they want to call it. Some people just call them mics. But it's one of the most common gauges that you're going to use in your career as a machinist or an inspector. And they're a very accurate gauge. They can get as they have resolution down to 1/10,000th of an inch here on the Vernier scale. So these are very accurate, very useful, and we're just going to focus on this one style, and then we're going to do another video about all the other different types of styles of micrometer out there. But we're going to focus on the outside mic. We're going to look at all the features, all the pieces, what to call them, how to calibrate them, the accuracy that's involved, how to handle them, and what they can measure in terms of GD and T. So let's just jump into it. So first of all, let's talk about the different pieces of the mic and identify them. And please forgive me if I say the wrong thing, because some of these things still trip me up every now and then. But as you see, number one is the frame. So just this large piece down here that you grip onto the micrometer with. Number two are the anvils. The anvils are what make contact with the part. So as you go to measure something, the anvils are what is touching the part. Third up there, the spindle. So the spindle is what's rotating here. It's the piece that moves in and out. Other styles of micrometers have non-rotating spindle anvils, but most OD mics are going to rotate as you twist back here. Number four, the sleeve. So the sleeve right here has got these etchings on them for the Vernier scale. It's got your distance traveled right here on the sleeve. Number five is the thimble. Thimble, basically where you want to grip it back here on this grip. Many thimbles are going to have a ratchet, which is shown as number 6. Some won't. It depends on the style of micrometer that you're using. I've got another style here that doesn't really have a ratchet back here. It's just a friction thimble. So there's some different styles, but if you have a ratchet, it'll go ahead and click every time you make a measurement. If you don't, you might have a friction thimble back here that'll help you make your measurement. Either way. Next up, number 7, you've got a lock here on the face. So when it's unlocked, you're freely able to move that spindle in and out. And when it's locked in place, I can no longer twist this. It stops the rotation of the anvil here. On this other micrometer I have here, this black one, it doesn't have a lock on the side here. It has a lock right here, this kind of a thimble lock, sleeve lock. So when you pull it, when you rotate it one way, it's completely locked. When you rotate it the other way, I can now freely move the spindle. So some styles of micrometers have the lock here with this ring, and other styles will have this lever right here on the front. Just take a look at what you've got. And then most micrometers are going to come with an adjustable wrench. So it could be different styles of wrenches based on the manufacturers, but yours should come with one of these here. Get that on the other camera. So this will help you do the calibration. And if you have a large micrometer above and 1 inch travel, you're going to get a standard. So this will help you set the calibration. This tiny little standard here. This is a 1 inch standard. It's the same thing as a Joe block. It serves the same purpose, but it's mainly for calibrating a micrometer, whereas Joe blocks can be used for many other things. And so just kind of get used to the terminology. I almost always mix up the sleeve and the thimble, call them one or the other. So just bear with me if I use the wrong terminology today. One of the key components of these micrometers is they have a rotational vernier scale, and that makes it very accurate. This style of measurement, vernier scale, allows you to read down to 1/10,000th of an inch very accurately. The downside to this is for beginners, it requires a little bit of math. You're going to have to learn how to read this vernier scale because it's not a direct reading that you can see instantly. You're going to have to add these numbers together in your head. And the more you do it, the more comfortable you're going to get, the easier it's going to get. It'll be second nature, but probably for the first month you use one, you may struggle and you may need to get out a piece of paper and write this down. Don't be afraid. Count lines. I have a video on reading the vernier scale, both the linear vernier and the rotational, and it goes into a lot of detail on how to read the vernier scale, including rotational micrometers. But to do that now would be a little bit too much time. So I've got this quick example up here on the screen. If you're going to go ahead and read what this micrometer is set for, you're going to have to add 3 pieces together. The first piece is the sleeve reading. The second piece is the thimble reading. The third piece is the vernier reading. So in this case, the sleeve reading, as you can see where the number 1 bullet is, it's reading 0.300 plus 2 lines. Every line on that micrometer represents 25 thousandths. So if you can see that 0.3 very clearly, you see 2 little lines after it, you can't see a third. That's why on the screen there, I have 0.3 plus 0.025 plus 0.025. That is what the sleeve is telling you. But you notice you're between lines. That second line you can see, but you can't see the third line. So you're between 0.350 and 0.375. Somewhere in between there. You don't quite know where unless you look at the rest of the vernier scale. So the second piece on there is the thimble reading, and that's going to tell you, it's going to get you a lot closer to where you are. So in this case, the thimble reading is 11, and what you're looking for is where that horizontal line on the sleeve intersects with one of the numbers on the thimble. So it intersects closest to the 11, right? And it's between the 11 and the 12. So that's one of the key things to remember is, have you gotten to the 11? Have you gotten to the 10? Have you gotten to the 12? You're always going to pick the lower numbers. So in this case, it's between the 11 and the 12. So we're going to pick the 11 thousandths. So when you add that to your measurement, you've got 350 plus 11 thousandths. You've gotten to 361. And then you're going to add the last piece. The last piece is going to be that 10,000th increment. And you're going to rotate your micrometer, and you're going to rotate it so that you can see the vernier scale, and you're going to try to figure out, there's 10 lines here. Actually, my mistake, there's 11 lines here because there's 2 zeros. And you're going to look for whatever one of those 11 lines matches up with one of these numbers here on the thimble. Only one of them is going to match up perfectly. And you're just going to have to rotate around and really look and decide which one lines up, and that becomes the third piece of your addition there. So that's 1,000th added to the end. When you add those 3 pieces together, you get 0.3611. So what I recommend you guys do, first of all, a good way to practice is to practice on something you always know. So grab some Joe blocks. You can grab some pin gauges here. If you've got a set of pin gauges, practice measuring those pin gauges and see what it looks like on your micrometer. But again, remember, check out that video on the vernier scale. If you're looking for more practice and more tips, we're going to move on to another example. Because what I want to point out, it doesn't quite show up well on the monitor, but there's a lot of confusion when you're near the 0 on the thimble scale. I've got 3 pictures there where we're really close to that 0 on the thimble. Let's see. Right here. So, hold on. Let me turn on the laser pointer. No, maybe not. All right. We'll just roll with it. So we're close to the 0 on 3 different occasions. How about instead we zoom that in on the second monitor. So I'm gonna bring this micrometer. I'm gonna give you 3 examples. We're gonna be near the point 3. Okay, this is gonna be your first example. I'm gonna lock this right on the 0. Okay, and we're gonna say that's right on the 0, 0.3. If you're having trouble seeing it on the second monitor, I am trying my best to get this to zoom in, but you can always pull up the camera feed from this one on the other video. So it looks a lot clearer on this camera here. So one of the tricky things is what happens when you're a little bit past the 0 or a little bit before the 0, and you're looking for how many lines can you see. In this case, I'm a little bit before the 0, right? And I can just barely see that next line, right? You're counting lines on the Vernier scale. And one of the downsides to the micrometer is sometimes you can see a line, but you shouldn't count it. So if you can see it, but you shouldn't count it, it might be in another situation just a little bit different. You can see it and you should count it. So how do you know the difference? What I do is I look at where the 0 is and where my scale lined up. So have I gotten past the 0 or have I not reached 0? In this case I have right here, I haven't quite gotten to the 0 yet. I'm between 24 and 0. So I know I haven't gotten quite to 0.3 yet, okay? Just a hair under. And when I move the thimble just a little bit past 0, now I'm between 0 and 1, and I know I've gotten past the 0, so therefore I'm at least 0.3 and maybe a half. You could look at whichever number lines up. I would say the 6/10 lines up perfectly. 6 or 7/10 lines up well from my point of view. So, but the problem is you can just barely see that 3 and that line. If I really exaggerate it, yeah, I cannot see that line anymore. But as I move further and further away, oh, I can see it. I can see it even as far as the 24, I can start to see it. So you don't want to count that line on accident. And that's one of the trickier parts of using a micrometer. So remember, just use some common sense, do some sanity checks. If you're not sure, grab your digital caliper and double check what you're doing. You're definitely going to see if you're off by 25 thousandths if you use a caliper. So don't be afraid to use that caliper to give yourself a sanity check as you are getting more and more comfortable using a micrometer and reading the Vernier scale. So let's switch back to the presentation. Get back to where we were. Now, when it comes to calibrating, first thing you're going to want to do is clean it. And there's a few different ways you can clean it. For me, I really like to use my finger to wipe off any oil, any chips. Personally, I've never had a problem with chips like cutting myself when I do this, but you do want to be careful. So let's bring up the second camera again. So I'm gonna wipe off this end, with my finger and wipe off the other end with my finger and just kind of grab any chips or oil. Now these anvils, when they're brand new, are very sharp. So I have once or twice, given myself a nice little paper cut on a sharp anvil, but never on a chip, funny enough. So that's a good way to do it. Another way that a lot of people do, I recommend you give it a try sometimes. If you're having trouble cleaning it off, you can grab a piece of paper. Any clean piece of paper will work, and you're just going to clamp on it with the spindle, and then you're just going to drag once it's clamped. And when you drag that paper through, it's going to remove any of the chips and dust and coolant that was on the anvil is going to get stuck in the paper, and that's a great way to clean it. So that's another great way. Once you've done that, check the rest of it. Check the rest of it's clean. You don't necessarily want to start calibrating it while it's still dirty. If you want to disassemble it, if you feel like there's a problem, all you got to keep doing is twist this off. It can sometimes be a little tricky to get back on, so I'm not going to, but this is pretty much what it looks like when you twist off the end. This is a spindle without a micrometer for it, but it's a very nice spindle. So this is, you could just keep threading it off until it slides all the way off your micrometer. So once it's clean, let's back to our steps. Oh man, don't know why it keeps doing that. All right, so now you're going to check the zero reading. So basically you're going to close the anvil and you're going to check that it reads 0. Then you're going to grab something like a Joe block, and you're going to make sure that it reads whatever the Joe block says. You're going to do that when it's all the way closed, right? When your anvils are all the way shut. You're going to do it again. Maybe about halfway through is a good point. Or you could do a couple of points in the middle, and then you're going to do one more at the extreme. So let's demonstrate that. So first of all, let's check it when it's 0. And I actually haven't done that before the video, so we're going to see if this one's still in tolerance. So I'm just going to very gently close it. If you're using a ratchet, the manufacturer is going to tell you how many clicks you should do. I believe Mitutoyo says 5. Personally, I've always been more comfortable with 3 or 4. And it comes down to the fact that you need to develop a feel with a micrometer. If you're not using a ratchet, you still need to develop the feel. So I could do the same thing without the ratchet and develop that pressure that I've developed over a long time of using a micrometer. I know how much pressure there should be and when it's closed. But if I keep turning it, I can certainly push that spindle even farther and get a false reading. So something you should practice with, again, Joe blocks, gauge pins, great things to practice your pressure with. So let's take a look if this one's at 0. I'm going to use the ratchet since we have one. There's about 3 clicks, and from the camera, it looks a little bit off, and from my eye, it looks a little bit off. So let me fix that for you before I check the other ones. And to do that, I think it's going to be easier for me to show you some pictures. So if you need to calibrate on every caliper, depending on the style, there's going to be a hole back here for you to put your wrench. There we go. So your calipers are going to come with a wrench, looks like this here, and you can use it to basically you're going to take the sleeve and you're going to physically move that sleeve. What I recommend, everybody's got a little different way of doing it, is close it where you think it's 0 and take a look either on the Vernier scale or or you can even just eyeball it. And you're going to have to move the sleeve that amount. So as you can see in the pictures here, first up, there's a little bit of a difference between 0. It's not quite lined up. Then the next picture, I identified where the hole is. The bottom left picture, we're putting the wrench in, and then we're going to pull. Okay, we're going to pull in the direction that we want the sleeve to move. So I'm going to try to demonstrate that. It may not show up well in video, but we'll give it a shot. So first thing, I would say 2/10 based on my eyeball. I think the 2/10 lines up fairly well. Let me take a look. Yeah, I would say about 2/10. So I'm going to try to move this thing 2/10, but I got to figure out which direction I want to go. I want that 0 to move downward relative to the thimble. Okay, we don't want the sleeve to go the other direction. We want the sleeve to move towards me if you're thinking about it that way. So one thing I don't recommend you do it with it closed. There's gonna be a lot of force involved and you might bump it while it's closed and damage the spindle anvil. So I would say open it one full turn and then try to eyeball it back to where you had it, or use the Vernier scale to line it back up. But this is gonna be kind of an iterative process. We're gonna grab that wrench, lock it in the hole, and then I'm gonna need to push this wrench towards me. So let me do that. I'm gonna stable my hands on the rock here, and it just becomes down to apply a little bit of force. Haven't moved it yet. All right, it moved. Probably can't see it move in the video, but we're gonna check how far it moved by closing. Oh, it moved a lot. I don't know if you can see that. It moved almost pretty much a full thousandth. So as I said, it can be tricky, it can be iterative. I'm now down to the 24. So I'm gonna put it back and I'm even gonna lock it so it can't move. And now I need to go the other direction. I moved it too far one way. Now I've got to move it back. So now I'm rotating the opposite direction. Hopefully, if you can't see it on the monitor there, check out this secondary camera feed. All right, I moved a little bit. I want to try to move it a tiny fraction more. Okay, moved a tiny fraction more. This is what it looks like before I close it, but it may not be this. It may not be exactly. So let's close it. All right, I'm still a little bit out of calibration. Right, it's not quite lined up with 0. So we're going to keep going. Unfortunately, this is like chasing your tail sometimes, but the more you do it, the more you kind of get a feel for how much pressure it takes to move this thing. You can apply a lot more force towards the end of this wrench and you'll get a little bit more control than if you try to push near the root of the wrench. So all right, I got a little bit more movement. That might be good. Let's double check it. All right. It's not perfect. I could be here all day. I mean, not all day, but we're going to move on. We're going to say, man, it's pretty close. It's not that far off. It's probably not as good as I would like it to be, but we're just gonna move on and check that it's check on that that's good. But as you can see, it's not easy. Well, it's not difficult, but getting it back to your perfect 0 can be a little tricky. So next up, I'm gonna grab 1/2 inch Joe block, and we're gonna measure a 1/2 inch and just make sure that it's reading correctly. Now, I haven't gone over how to hold a micrometer yet because this is kind of our first reading, really. A great way to hold a small micrometer is to wrap it with your pinky so that you have full flexibility with this hand to turn it, and you can use your other hand to hold the part, whatever you're measuring. So I'm going to do that. And I'm not using the ratchet. I can't quite reach the ratchet with the way I'm holding it now. So I'm using my touch and reading right about 0, which means we're reading right about 500, which is what we wanted. Didn't quite get to 0, but also didn't quite get to 0.5 either. So I think we're okay. And then we're going to do 1 inch. I'm going to do a full travel check. So grab the 1 inch block. I know this is 1 inch. And same thing, I'm holding with my pinky and I'm using my touch. And what's that read? Reads a little bit over, just a fraction over, maybe 2/10 or 3/10. So it's a little worrying, right? I did 3 different measurements and I got one. Let's see, I don't remember my 0. Let's do our 0 again. Little bit above 0, right? And then at 500, I got pretty much 500, 500 thousandths. So there's a little bit of play in this micrometer, probably more than we would like. Looks pretty good, maybe a hair over. So overall, I say it's in pretty good condition. It's not in the best condition, but it's also not a new micrometer. This has seen some use. It's not unexpected. It's probably just on the edge of tolerance in terms of repeatability. But I would say it's probably good enough to use, but I say probably just because trying to do this on video and we're not measuring any real parts, but check your manufacturer specs, check your calibration requirements, see what kind of accuracy you need out of the calibration, because you're never going to be perfect, dead on perfect, but just need to be close. I would say if you're within 1/10,000th when you're doing your 0 and you're checking all your points, you're good to go with that micrometer. All right, so let's jump back to our presentation. All right, so we skipped ahead. Let's see if we did all of our steps. Oh yeah, so what happens if you get a really drastic difference? I got some very small differences in those 3 readings, but if you get a big difference, you've got a problem. The frame is most likely bent. These things can bend, especially as they get bigger and bigger. They can get up to 20 inches, 24 inches. They can get really big. I've heard stories of 70-inch micrometers, 2 or 3 people needing to handle them to get one measurement. So these frames here can bend if you apply too much force one day. The spindles can also get damaged. So you want to be careful to inspect these, make sure that they are flat, there's no chips in the spindle that might be throwing off your reading. And overall, just look for any damage at all that may be affecting your micrometer accuracy. Unfortunately, if you've got a problem, like damage, replacing that one part, it might be cost effective, but it might not be. It may actually be more cost effective to replace the whole thing. Getting replacement parts is almost the cost of a new one in many cases. So just treat them gently, treat them carefully. A small 1-inch micrometer might range between $70 and $100, and they'll get more expensive as they get bigger. But typically from 0 to 3 inches, 0 to 6 inches, they're pretty reasonable because they're pretty commonly available. So just try to remember that as you try to keep them in good condition so you don't have to replace them often. One more thing I forgot to mention. I used a Joe block to check calibration, but every mic above an inch in size, like this one, is going to have the calibration block that comes in the case, and you can use this to set calibration on anything that's above 0 to 1 mic, because obviously I can't zero this out. So let me show you how that works. Since I can't physically close this micrometer, right? This gap's always going to be here. The manufacturers provide a 1-inch distance for you to use. So when you're doing that, you treat it just like it's a Joe block, and then as you're closing it, if it spins like this and it's not wobbling and it's actually even like, staying in there with the little bit of pressure you applied, you check your zero. Looks pretty good to me. I wouldn't even change it. But that's the key. If you've got sometimes these get very long. If you have a 5 to 6 micrometer, you're gonna have a 5-inch standard. If you have a 12-inch micrometer, you're gonna have a 12-inch standard. So when you're using one of those bigger ones, if it's wobbling around a lot, you just haven't tightened it down enough. So look for it to spin smoothly like this. It may not spin exactly on center because you're not going to be able to hold it exactly on center, but as it spins around and it feels smooth, you check your zero. So that's why the micrometers come with one of these, so that you can check and set your zero. You can use the same wrench. It's the same procedure no matter how big your micrometer is. All right, let's continue. All right. So we've gone through checking at 0, checking halfway through, checking at 1 inch. We've gone through an adjustment. And now we're going to switch gears a little bit. We're going to talk about how accurate micrometers are. So your typical bidirectional accuracy is going to be 1/10,000th of an inch. That'll be true for most micrometers that are less than, say, 3 inches. But you'll want to verify with the manufacturer of the micrometer to be sure. When they get above 3 inches, they also tend to get a little bit more accuracy error. So it'll grow as the micrometer size grows. I'd say, 1/1000th and 50 millionths when you get above 3 inches to 6 inches, maybe 2/10,000ths above 6 inches and 3/10,000ths above 12 inches. It follows that general trend. And accuracy error is going to be kind of dependent on how big everything gets. It's length dependent. So bigger thing you're measuring, more error you're going to have. It's the same as with a caliper. It's the same with the CMM. Same with every tool. More you have to travel, the more error you get. So then the next question is, well, when can you use this? When can you not use this? And my tolerance threshold to use a micrometer is about 1/1000th of tolerance zone. So that's actually a very small tolerance zone if you only had 1/1000th. If you had larger than 1/1000th, you could still use a micrometer. If you had less than 1/1000th, that's debatable. So there's not very many gauges that are more accurate than this. So you may still need to use a micrometer, because an indicator, it's not going to give you that much better accuracy. A CMM might, and it might not. It all depends on the part and the feature. But in comparison to a caliper, if you've seen the caliper video, I said that you want to use a 10,000th tolerance zone so that you use a caliper. That's the minimum. And with a micrometer, it's only 1/1000th. And if you see this graphic here, that basically on the bottom bar that goes from red to yellow to green back to red, Each one of those squares is 1/10,000th of an inch. So you want your measurement to fall, in the middle of that zone, and then you do your plus or minus. In this case, I put two 10,000ths. So as you get closer to one of the edges, left or right, close to those warning signs, again, it's just like a caliper. You might be out of tolerance. But because you're talking about a 10,000th of an inch, it's usually not an issue. You're either in tolerance or you're not in tolerance. Every once in a while, when you start talking about manufacturing things with 1,000th of tolerance zone, you're going to get a lot of parts right on the edge, and you're going to have to make sure your micrometer's calibrated, because your micrometer might tell you, yeah, you're 1/10,000th within spec or you're 1/10,000th out of spec. And that's a very, very small increment to accept or reject something. So that's one of the challenges of precision manufacturing, is sometimes it comes down to the accuracy of your gauge, the accuracy of your machine, the environment you're in, all of that working together. So we've talked about some handling already. I've mentioned, the smaller mics. You can kind of grab it with your fingers in the frame here. Another tip, I've seen some people, they'll kind of roll it on their arm to quickly, move the spindle, and that's okay. That's a great way. That can be a good way to close it. But you can, if you're not paying attention and you really drive this thing home, sooner or later you're going to damage something on the internal. So be careful when you're doing that. But you might see some people doing it. When you are going to put these things back in the case, especially a 0 to 1 micrometer, what you don't want to do, switch the video. What you don't want to do is put these back in the case when the anvils are closed. So there's a few reasons for that. One of the reasons is going to be if it's closed, sometimes due to the temperature variations, the heat variations, this thing will start to expand. And when the anvils are closed, they have nowhere to go and the pressure builds up, and you could damage some internals in the backside. That's one of the reasons. Vibration, just from carrying this thing around in a case in a car, it's the same issue. There's nowhere for this thing to go if there's a bad vibration. So what you'll want to do, I would say, leave about 1 rotation or even 0.1 of an inch, and then lock it in place so that it can't rotate on you in the case, and set it in the case. Sort of skipped over some of the other reasons. If these anvils are closed and touching, sometimes rust can develop between them because they're touching, and there might be just the slightest air gap, and there might be just the slightest bit of moisture in the air, and you'll get some rust accumulation there. So that's another good reason. But I would say leave about a 0.1 gap is a good way to still fit in the case and leave a nice gap so that you don't have any issues. And remember to lock it down and don't leave them closed. And some other tips, just like with a caliper, if you've watched that video or any of these other videos, the amount of pressure you apply is important. So as I measure this diameter here, let's see if I can do this on the camera real good. If I apply kind of a weak pressure, that's kind of a weak pressure. I'm at a 0.750, and let's say it's 3 or 4 tenths. Again, we're in that danger zone of, am I past the 0 or am I before the 0? Well, I know I'm between 0 and 1, so I'm past the 0. I'm seeing 2 lines, so I'm at 750. And then I'm gonna, got kind of a, you can see it definitely stopped, but it is wiggling through. I could apply more pressure, and now I'm at 750. And I could apply even more pressure, and now I'm at 749 and about 8 tenths. Let's see if you can see that. 749 and about 8/10. So just on the variation in pressure, you can apply a few tenths of extra pressure and get a bad reading. So you want to develop that pressure. You want to use the ratchet. If you have a friction thimble, it's similar to a ratchet, but it won't make a noise. And your thimble is just going to spin as soon as it meets a resistance from your part. So the ratchets are a great way to get even, consistent pressure that doesn't involve person to person, whether you're tired or whether you're holding it at a weird angle. You know, the ratchet is always going to go at the same pressure. A lot of people don't trust the ratchets, and I understand. My philosophy is to always just know what you're doing, know what it's capable of, and make the decision yourself whether you're going to use this ratchet or whether you're going to go by touch. A lot of machinists who've been doing this a long time, inspectors, they prefer to go by touch because they've got that experience and they don't have necessarily experience with the ratchets. Especially a new ratchet, a new micrometer you've never used is going to have a different feel. So I understand that too. And I just want you guys to know what your options are. Don't blindly trust your ratchet. Don't blindly trust your feel. You know, be paying attention and observant of what's going on. So let's jump back. And remember, you know, it's not a huge consideration, but the more you handle this thing, the more you're going to warm up this micrometer. And it's made out of very temperature stable materials, but every material expands with temperature rising, contracts with temperature falling. So, and some very, very precise measurements that have very small tolerances. I've been handling this for about half an hour now, so we want to be careful about how long we're handling it, and if we're maybe changing the temperature, even where we're touching it, whether we're touching it on the frame or touching it here on the spindle, which is metal. This frame is going to be a little bit more temperature stable, so try to handle it there as best you can. And then when you set it back down on the cool granite surface, it's going to be changing temperature again. The heat is going to be moving into the granite. So not a big consideration. I haven't really run across it in my career. Some people I've talked to have. So just be aware of it. Try to minimize it when you are dealing with a very, very tight tolerance. Now, I've already talked about developing a feel. But when it comes to these big mics, if you're ever working with a really large mic, man, that can be difficult. I've had to do that a lot. And one of the trickiest things is, are you registering correctly when you've got a big diameter and you've got these tiny spindles? These spindles are the same size as this micrometer. They don't get any bigger. So I have a couple of suggestions, whether it's big or small, when you're trying to decide if your spindles are registered. You kind of want to rock that part into place. So actually, here we go. We're going to demonstrate this. I can't demonstrate it with a huge mic, but we can do it with this 1 to 2 mic. So first of all, if I'm trying to take this measurement, right now I'm too small. The part definitely won't go in there. So we're going to open this up, and then, okay, now it can definitely go through. And now we're going to kind of close it up. And then as I'm closing it, let me open it a little bit more. As I'm closing it, I'm going to pivot the part back and forth this way. I'm going to slide it in and out this way because I need to register both in this direction and this direction to get a good reading. And when you have very large parts, sometimes people tend to be at a different plane. This is kind of an exaggerated example, but they'll be at a different plane, and because they can't see everything, their ratchet is stopping and they're just at a weird angle. So it helps to twist either the micrometer up and down or the part up and down and slide it in and out and slowly move in the part. All right, so we're getting closer, and I'm not even really looking, I'm kind of just feeling it. Okay, I've got a good feel. I can't twist it anymore. It's definitely registered that way, and I'm trying to rock it through. I'm gonna open it up a tiny bit, and there we go. When it kind of slides through, you're gonna get that nice, like almost a suction cup finish, as it slides through just perfectly. We'll lock it down and we'll read it at 1.225 plus 6,000, so 1.231. Let's see if no shame in double checking with the caliper. So caliper gave me 1.230. Micrometer gave me 1.231. I'm going to trust the micrometer because it's a more accurate measurement device. But I know I'm in the ballpark. I didn't add it wrong. So when you're working, when you're up with a large part, if imagine this micrometer I'm holding all the way out here, you're going to want to rotate it horizontally and twist it this way, right? And go in and out. And then, as you get closer and closer and closer, it's going to be harder to move it. You're going to be able to slide it back and forth. Once you've got the twist out, it'll be easier to just slide it back and forth and get your final reading. All right. So that's basically the same procedure I just showed you, whether it's big or small. Try to practice that with some round parts and some gauge pins. It's my go-to. Keep practicing on things you know. And then cleaning. We've talked about cleaning already. It is okay to rub these a little bit with a solvent, a very light solvent, but you don't want to soak it or blast it with compressed air. You don't want to, dunk it in anything. But if we need to clean off some sticky coolant, some sticking oil, it's okay to use a light solvent. Every once in a while, you may need to disassemble it and put a drop or two of lubricant on the screw here. I'll show you that. So as you take this apart, if you keep unscrewing, there we go. We're going to expose this ball screw. It's very accurate ball screw. Can see it down there. There it is. So you can put a couple drops of lubricant, a special spindle lubricant, and that'll help you get a nice smooth motion here. If it feels like it's sticking, you can take it apart. Make sure you're using lint-free cloths, rag or not rags, but wipes. Make sure you're not leaving anything behind. And just 1 or 2 drops usually is enough. You don't need to put a lot. Definitely don't. It's easier to add an extra drop than it is to take one off. So last thing we're going to talk about in terms of micrometers is what GD&T can this do. So first of all, you can do a circularity, which I will demonstrate. I will demonstrate that now. So it's just like with a caliper. When you want to know how circular something was, you just go around at the same plane. Here we go. So I'm reading, what am I reading? I'm reading 0.516, and we will say that's 8/10. So 0.5168. That's one of my readings. And then we're going to rotate the part and we're going to check another location. And we're going to say 0.518. We'll call that 2. So I've got about 4 10,000ths of error already just going around. And now I'm at 0.517. call that 6. Um, so as you just go around at the same plane on a circle, you can get the circularity error. Circularity error is going to be the difference between your smallest reading and your biggest reading. So take those high numbers and those low numbers, do a subtraction, that's your circularity error. The other thing you can do is you can do parallelism. Here we go. So with parallel surfaces, you can check how parallel is this face to this face, right? If you check the print, I don't believe there's a parallelism call out, so it's just going to fall into a plus or minus 5 thousandths thickness call out, but that means you should be parallel within 10. And let's see what we've got. Right now, I've got about 1 inch, just a bit less than 2 thousandths, say 1 inch, 1 thousandth, and 8 tenths. And then over at this corner, see what that is. Ooh, 1 inch and about 5 tenths. That's a big difference that's already happened. That's about 1 thousandth and 3 tenths. So let's check this corner. Again, I'm doing this by feel. Ooh, this is down to 0.997, no, 0.998 and 2 tenths. So there's a big parallelism error. Well, relatively big. That might be perfectly fine for this part. But I'll take the biggest number I saw, which was above 1 inch, and the smallest number I saw, which was below 1 inch. And we will get our parallelism error. So it's not the best way to do parallelism by far. An indicator and a surface plate is going to do a much quicker, faster, easier way. But sometimes when you have your part in the machine, you can't take it out and do a parallelism check. So this can be a good way to. I saw there was a problem right away, and the caliper would do the same thing. You can see a problem right away. If it's a tight tolerance call out, this one doesn't have a tight tolerance call out, so we're going to say it isn't a problem for this part. But that's a couple of things, couple of GD&T features you can check with just a micrometer, no other tools. So in summary, I just want to stress it is an extremely accurate tool. It might be the most accurate one you're going to work with because, like I said, a $70, $100 micrometer can get you 1/10,000th of resolution. And other gauges that do that are going to be just as expensive or even more expensive. So you're going to be using these a lot. Any parts that you're turning with a lathe, this is going to be a go-to measurement tool for anything that's a tight tolerance outside diameter. The downside, compared to our calipers, this OD micrometer can only measure something on the outside. It has no other measurement functions to do internal features, distances, nothing like that. So you're really limited to just outside features, but that's okay. You just might have to buy more of them because the range typically only 1 inch at the most, no matter what style of micrometer you're looking at. You can calibrate them in-house with calibrated Joe blocks. So that procedure where we went through and we checked 0 and we checked halfway through and we checked the full distance. Well, if you're using calibrated Joe blocks that have a traceability, you can calibrate this micrometer with those. You're going to want to also check for damage on the spindles, as well as close them and look for any light, which you really shouldn't see like you do with a caliper because these are so small. But if you do see something, you've definitely got a problem. And then last thing, there are digital micrometers for sure, but they're expensive. They might be 2 or 3 times the cost, and you're really going to need to get comfortable with the Vernier scale. Like I said, it took me about a month to really get comfortable to where I didn't need to write things down and I didn't need to count out loud 1 line, 2 line, 25 thousandths. But eventually I did get there, and it's really critical if you're going to be using these every day. Just practice a bunch. So thank you for watching this video, and I hope you enjoyed learning about the outside micrometers. Please check out my website, pragmaticmetrology.com, for any more videos related to many other gauges and concepts that are important in inspection and metrology. And I want to thank the Laney Machine Technology Program in Oakland for providing these parts that I could use and a lot of these tools. It's a great program. I recommend you check it out if you want to learn about manual machining, CNC machining, inspections, mechanical drives. They have many courses. They have certificates you can earn that will be a great resume booster for your job search. So please check out the Laney Machine Technology Department in Oakland. And thank you, and I will see you for the next video. Bye.